let's learn today about vectors. However, before going into that, I would like to emphasize the difference between vectors and what we call scalars. So let's first understand what these things are. Scalar is used for quantities that have only magnitudes. So let's first start with scalars. For quantities who only have a magnitude. For example, mass. If we have an object, like for example, if we have a ball, and this ball has a mass of, 2 kilograms, we refer to mass now as a scalar because it has only a magnitude, which is only a number. Yeah, it can be an integer or non-integer, doesn't matter. It can be like 2.2 kilogram or whatever. But what matters here is that it has only a magnitude. The other example would be temperature. The temperature of the room is also a scalar because it has only a magnitude. The room temperature here is right now 23 Celsius degree. Okay? So that's what I mean by a scalar. However, we have also some quantities that are not only scalars. These quantities, to represent these quantities, we would then use vectors. What do they have apart from magnitude? So not only they have this magnitude, as before, they might also have a direction. And that's where the vectors are very useful. An example could be, for example, displacement. And now why displacement is a vector? For example, if I am moving from point A in a space to point B, and if the distance between A and B, if this distance is 2 meters, now if I move from point A to point B, I might show this displacement from point A to B with a vector like this. Now this vector has a direction in this direction and a magnitude of 2 meters. So I can show it as like a vector like this. Yeah, and let's show this, the name as X, the vector X. And we show usually the vector by a little, arrow here. Or in some books, they show it so either with like an X with a vector on top, or some books like to show it with a bold character. Here I actually like to use this little arrow. I find it cute. Okay, so we use this vector X to show the displacement, and then the magnitude of X, which we show like this. This is the magnitude of X. Here is 2, because it is 2 meters from A to B. Now, if we went from B to A, then we would, if we go from this point now to this point, then we would end up with a vector like this. Yeah. Now the other vector, let's show it with another name, like the vector Y, let's say. It has the opposite direction of X, but the magnitude of Y, if we go back again to the point A, is again 2. So they have the same magnitude, but they have the opposite directions. So now it's clear why it's very important to use vectors, because we are not dealing with only magnitudes, but also directions in a space. Are there other examples for vectors? Sure, there are many quantities for which we use vectors to analyze. For example, force, velocity, many examples, momentum, angular momentums. We will talk about all this later. But so for now, we understand the difference between vectors and scalars. Okay, now let's see how we actually show a vector in a, let's say, Cartesian coordinate. So, for example, imagine two-dimensional Cartesian coordinates like this. And this is x direction, this is the y direction. Now, you might have heard of something called unity vectors. Unity vectors are vectors in the direction of each axis, x or y, and they have a magnitude of 1. And we can represent all the other vectors in this space as a combination of a linear combination of these unity vectors. Okay, now I go into details more. So imagine here we have our x direction. Now I have a unity vector here as I. And same here in the y direction, I have a unity vector j. And for some reasons in books, they like to show these with I hat and j hat. Again, each of these has a magnitude of 1, and they are perpendicular to each other. So I and j are actually perpendicular to each other. Now, any other vector in this space can be represented as a linear combination of these vectors. So, for example, let's make a vector here in like this, okay? And let's call our vector A. A is a vector in this space of x and y. And if we project A onto these two axes, x and y, then we end up having a component of this much on the x-axis and a component of this much on the y-axis, right? Now, how do we write this? So, for example, the vector A equals some component here. For right now, we don't know how much it is, yeah? But we call this A of x, and here we call this A of y. So we have A of x times I hat. So we have A times A of x, this much, in the direction of I hat, which is the unity vector of the x-axis. And at the same time, A also has another component, which is AY times j hat. And now that is how we represent a vector in this coordinate. To make it clear, let's say a numerical example. So, for example, we have a vector here. Let's call it B. And this is X, this is Y. And here, let's say, numbers are not to scale, but just an example. Let's say here is 3 and this is 2. So I can write the vector B as 3i plus 2j. Okay, so now we know how to represent vectors in terms of the unity vectors. Now, you might ask, okay, now we have this vector, we know its direction. What is now the magnitude of the vector? And the answer is, the magnitude here of the vector A, I write it like this, as the absolute value of A is this component in the x-axis, so ax squared plus ay squared, and then we take the square root of it. If we do this, then we have the magnitude of vector A. Cool, no? Okay, so for example, in our example, the B vector, 3i plus 2j, what is now the magnitude of this? So we can write the magnitude of B is 3 squared plus 2 squared, and then the square root, which is equal to 9 plus 4 square root. And that is the square root of 13. This is the magnitude of vector B. Right. Very similar to this, we can also expand this to three-dimensional vectors. What if we have a three-dimensional vectors? Well, it is very, very easy. Now, imagine we have a three-dimensional Cartesian coordinate. And this time I write here, this is our x-axis, y-axis, and z. Yeah? And so here again, very similar to here, that we had I and j as our unity vectors. Now we also need a third one in the direction of z. Yeah? Okay, so how do we do this? Let's just sketch our unity vectors. Here I have my I hat. Again, I have my j hat in the y direction. And it's common to call this a k hat in the z-axis. So we have our I, our j, and k as three unity vectors. And don't forget that these three are perpendicular to each other. Yeah? Okay. Now we have any arbitrary vector in this three-dimensional space. For example, let's choose blue, and let's say we have a vector like this called C. Yeah? And C, if we project C into the space of x and y, what do we get? If we do it like this, then we have a point here, then I do it like this. Yeah? So if we do it here, this vector C is now projected here into the x and y space and has a subcomponent of cx, which is this much, yeah, and then another cy, so I will call this cx, yeah? Cx I hat, and then cy in this direction till here, j hat, and then from center to this point we have also the ck, k hat. Yeah? So we can actually write this vector c as a linear combination of three vectors, cx, cy, and cz, or the value of components in each direction, and then we might write the vector c as cx I hat, cy j hat, and then cz k hat. Yeah, and again, very similar. If one wants to calculate the magnitude of c, then it's easy. Cx squared, cy squared, cz squared, and then you take a square root of this, and this is the magnitude of this vector. Perfect. So now we know how to represent vectors in 3 dimensions. Okay, now let's also talk about some operations we can do on our vectors. That would be really cool, no? So what are the simplest operations? For example, if we have a vector A, we can multiply this vector by a scalar, for example, alpha. And then we get what? We get a new vector. Let's call it B. So the vector B is vector A times a scalar. And let's remind, scalar is a quantity that has only a magnitude. So scalar alpha here is just a number. It can be 2, it can be 2.3, it can be -2, yeah? It can be any number, but it has no direction and it's not a vector. And we can simply multiply a scalar to our vector and get another vector, yeah? So this is easy. So for example, if we have, let's say our coordinate like this, again x and y, and if we have a vector, let's say in this example only in x direction, it is a, yeah, this is our vector A, and I don't know, let's say A is 2 I hat, so it's 2 times unity vector in the x direction. And now we have alpha. What is alpha? It's a scalar, so let's say it is 3. Why not 3? No? Okay. Now what is B in this case? You might wonder. Okay, we said B is alpha times A, so it is 3 times our A, which is 2 I hat. And what do we get? It is 6 I hat. And now that, how do we now sketch the vector B in this case? So 6 I hat, it means it is in the same direction as A, but it is 3 times bigger. So if this is A, yeah, I would, for example, sketch B like this. Now this is my vector B. It's 3 times bigger than A. Now you might ask, okay, what if alpha is negative? Don't worry, it's the same thing, it's just in the other direction. So for example, if in this example, if alpha is negative, it is, for example, -1. Okay, so again, let me sketch quickly. X, Y, yeah. And then I have my A vector. But in this case, alpha is -1. So what are we gonna get? So B is -1 times A. And A is 2I. So B is -2I hat. So it is the vector B is, it has a magnitude twice of A, but in the direction is in the negative direction. So I can sketch it like this. So it's here, here, to here. So it's twice, but in the other direction. Easy. Okay, now what else can we do with our vectors? We can do additions. So I mean addition of two vectors. And obviously we can also do subtractions. Because why not? Subtraction is a kind of an addition just with a negative sign. Yeah? Okay, now let's try an example. If we have a vector A, and we have also vector B, we could have a vector C, which is A plus B. Or we could have, for example, vector D, which is a subtraction of these two, which is A minus B. Now, what is really the difference here? This addition and subtraction? Nothing. It's addition. It's subtraction is kind of an addition. You just have a scalar of -1 here. Yeah. So we could also write this as A plus -1 as a scalar, and then times B. Yeah. So that's why I'm saying the subtraction is actually a kind of an addition. So not a big deal. But what I want to add is that we cannot, it's not that we only do this easy addition and subtraction of two vectors, but we can also extend this to any linear combination. Yeah. So for example, I can define my vector, let's say again, C, as a scalar, let's say alpha times A plus another scalar, let's say beta times B. Now here the vector C is a linear combination of A and B vectors. And of course, we also don't limit ourselves to a linear combination of only two vectors A and B. We can have many, many vectors. Huh? So, and that means, for example, we could have an arbitrary vector C, or let's say E, as a linear combination of many vectors, like for example A, beta, B, I don't know, gamma, C, and you know, in mathematics we like to make some short formulas for such infinite number or series. And so why not writing it like, for example, A of n, and then we have a vector A n, and then we are summing all these together, yeah? So then I put like a summation of n, and then we call this E. So, and that is just a nice way of writing the same series, just instead of writing all these, because n can be like an infinite number from I don't know 1 to n, and n could be anything. Here I'm just saying we have an infinite number of vectors and we are adding them together. So each is multiplied by some scalar and then a vector, and then at the end we will sum all them up together. Okay, now can we make an example, a very simple example? Yes, why not? Okay, so let's say we have a vector a1, and I like to write this as let's actually say we use only numbers here. Yeah, so for example, our vector a1 is 2i plus 3j. Yeah, then we have another vector 2, and this is I don't know, 4i minus 5j. Now if we have a vector c, which is this is a funny way of naming them. I could write this as yeah, we could write this as just a and b. Yeah, this is better. And then we define a vector c as a plus b. And so what do we get here? Yep. So I can write c as the multiplication, the addition of the numbers in the I hat direction. So 2 plus 4 is 6 times I hat plus. Then here we have a minus 5 and a 3. It gives me a minus 2. So minus 2 j hat. And so we could sum up the vectors a and b and get the vector c. And here, if you want, you can also calculate the magnitudes, just as we described previously. So as a quick conclusion, let's go back to what we said. So we said, what are vectors? What is actually the difference between a vector and a scalar? Scalar has only magnitude. For example, the temperature of the room is 23 degrees. This is just a number. It has no direction or anything else. It is only a magnitude. However, vectors have magnitude and the direction. It's if for a displacement, if we are having a car and we are going to a road, it's not enough to say that we moved 3 meters, yeah, because we can move in any direction. Now if you want to tell me from point A you went to point B, it's not enough to say that you just moved 3 meters. You should say I moved 3 meters in the x direction. Then I know where you are. That's why for vectors we also need a direction. Yeah? So you see how important and useful it is to use vectors in this example. We also mentioned how we can use our unity vectors to represent any vector in the space in terms as a linear combination of these unity vectors. For example, here the vector a in terms of I hat and j hat is written like this. And we can also calculate the magnitude of the vector. Same thing in the 3 dimension as we explained. We can just expand it to higher dimensions as well. We can do operations on the vectors. For example, any vector can be multiplied by a scalar and then you get another vector. or the addition or subtraction of the vectors, which is very fun because we will get another vector easily. Now, how to calculate it is also explained here. So basically, you do a linear combination of the vectors, and then by adding or subtracting the relevant components in each direction, then you get a new vector.